Good morning, ladies and gentlemen. Welcome to our Monday lecture for WTW 124. We are about 9 minutes early, so the lecture will start at 9:30. In the meantime, what you can do is try out the following long division, or in other words, find the quotient and the remainder of division of this fourth degree polynomial by this second degree polynomial. So we are about 8 minutes early. Lecture will start in just about 8 minutes time. Please bear with us. Okay, good morning, ladies and gentlemen. Welcome to our Monday lecture for WTW 124. So, as usual, just a little bit of housekeeping. Please take note of the announcements that go out on Monday afternoons. Those announcements have all the information that you need to be able to participate in WTW 124. Then also let me state that yes, there are tutorials this week. If you need help on the final homework, which I believe is homework 14, then please do attend your tutorials. And then, as usual, I will do my best to keep an eye on the chat. So if you have any questions during the lecture, please post them in the chat. But I do ask that we keep the chat on the topic that we are actually currently discussing. Okay, so before the lecture started, I posed this long division problem that you could try. Dividing a fourth degree polynomial by a second degree polynomial. So long division, all that it takes is a little bit of practice. So do make sure that you get enough practice in doing polynomial long division. And it really shouldn't take you too long to do a long division, like a minute or 2 minutes. That is how long it should be taking you to do polynomial long division. Make sure that you're practiced with your mental arithmetic. That also helps. Okay, so on our previous lecture, we discussed some strategies to find roots of polynomials. So strategies to find all the roots of polynomials. So first of all, the fundamental theorem of algebra tells us how many roots we're looking for. So how many roots are we looking for? All we do is we look at the degree of the polynomial. That tells us how many roots counted with multiplicity we are looking for. And then what we can do is we can guess some of the simple roots. So we can guess and use the remainder theorem and the factor theorem to find some of the simple roots if the polynomial actually has some of the simple roots. So what we will do is we will guess or we will try 1, plug it into the polynomial, see if we get 0. If yes, then we have a root of the polynomial. If no, 1 is not a root. Then we will try -1. See if we get, plug it into the polynomial, see if we get 0. If we get 0, yes, then we have a root, then -1 is a root. If no, then we have to move on. And we can try I and -I. So what we can do is we can guess some of the simplest roots that the polynomial may have. The next strategy that we have is if we have real coefficients in our polynomial, then we get roots for free. And what do I mean by we get roots for free? That is because if our polynomial has real coefficients, so no i's anywhere in the coefficients, if we have a complex root, then the complex conjugate of that root is also a root. But again, I stress the polynomial must have all its coefficients be purely real numbers. There should be no complex parts to the coefficients. And the next strategy is grouping. So if there is some special kind of grouping of the terms that we can exploit in our polynomial, that also helps. And our final strategy is if we have a factor whose which has the form x to the n minus c, then this factor, the roots corresponding to that factor are of course all the nth roots of c. And we've seen in chapter 6 how to compute the nth roots of a complex number c. Okay, so here we have the strategies that we could use to factor polynomials, or equivalently to find the roots of polynomials. And let's jump in immediately and get our hands dirty. So let's take a look at an example. Find all the roots of the following polynomial. F of x is equal to x to the 4 minus x to the 3 minus 5x squared minus x minus 6. Okay, so firstly, let's take a look at the degree of the polynomial. The degree of the polynomial is 4. So by the fundamental theorem of algebra, we're looking for 4 roots counted with multiplicity. By fundamental theorem of algebra, f of x has 4 roots counted with multiplicity. So some of the roots can be repeated. Okay, let's take a look at our polynomial. I don't see any pattern here. So let's start off just by guessing some of the roots. So let's guess some roots. Okay, so let's try and see if 1 is a root. So if we plug in 1, what do we get? We get 1 minus 5 minus 1 minus 6, and that is minus 12, and that is not 0. So 1 is not a root. Okay, let's try minus 1. So let's try minus 1. That is, how does it go? That is 1 plus 1 minus 5 plus 1 minus 6. And if we work that out, that is also not 0. So minus 1 is also not a root. Not a root. Okay, let us try I. So f of I. And if we plug that in, what we get is 1 plus I plus 5 minus I minus 6. And what we get is we get 0. So we have I is a root of f of x. Okay, so now we have a root. We have one root. And notice here our root is a complex number, I. Let's take a look at our polynomial. Notice here, coefficient is 1, minus 5, minus 1, minus 6. All of the coefficients are real. So all of the coefficients in our polynomial are real numbers. So that means we get a root for free. So since all coefficients of f of x are real, minus I is also a root. That is because the complex conjugate is also a root, and the complex conjugate of I is minus I. Okay, so that means that the following polynomial is a factor of f of x. And we've already factorized this factor, so we need the other factor. So now we need to perform long division. So let us work out or expand this polynomial. This is x squared plus 1. So what we will do now is we will divide our polynomial f of x by x squared plus 1. So that is x to the 4th minus x to the 3 minus 5x squared minus x minus 6. Okay, now we can do our long division. Actually, we've done this long division on Friday. So take a look at Friday's lecture, the long division that we had to try or that we were invited to try at the beginning of the lecture. So we do our long division. We get a remainder of 0. That is because this polynomial we know is a factor of f of x. And here is the quotient. So what do we now know? We know f of x is equal to x plus I, x minus I, multiplied by the quotient, x squared minus x minus 6. Okay, and here we have a nice quadratic, and in fact this quadratic factorizes very easily. So let's factorize that quadratic. That is x minus 3 x plus 2. Okay. And here we have now factorized our polynomial f of x into 4 linear factors. And notice here, from the fundamental theorem of calculus, not calculus, of algebra, we're looking for 4 roots. And once we've factored our polynomial, we can read off what the roots are. So the roots of f of x are, and what are they? They are minus I from that factor, they are I from that factor, 3 and minus 2. So 3 from there and minus 2 from there. And here we have found all 4 roots of f of x. Okay, so let's just go through that again. So what did we do first of all? We took a look at our polynomial. We didn't see any useful pattern that we could exploit. So what we started with was guessing some roots. So try 1, plug it in there, see if we get 0. If we get 0, then we know that 1 is a root. So we plug it in, we get minus 12. Minus 12 is not 0, 1 is not a root. Try minus 1, same thing, we get something non-zero, so minus 1 is not a root. We try I, and then we immediately see, we get 0, so I is a root. So we immediately get that I is a root, so we know that x minus I is a factor. But also, since the coefficients of f of x are real, we get another root for free. So the complex conjugate is also a root. So we know that x plus I is also a factor. So if we multiply these two factors together, the result is also a factor of f of x. So if we divide f of x by this, then we get the remaining factor of f of x that we should still factorize. So we do our long division. We should get a 0 remainder, otherwise we made a mistake previously somewhere else. So we do that, and we see that the quotient dividing by this factor is x squared minus x minus 6. So there is the quotient, and that one we factorize fairly easily. So we find the 4 roots of f of x, which is minus I, 3, and minus 2. Okay. Let's take a look at another example. Example. Find all the roots of f of x, which is defined as x to the 9 plus x to the 5 minus x to the 4 minus 1. So find all the roots of this 9th degree polynomial. So first of all, by the fundamental theorem of algebra, f of x has 9 roots, counted with multiplicity. So if we find 9 roots, then we know that we have all of them. There is a question in the chat. Let me just take a look at that. Karabo asks, what if we did not find a complex root? In that case, do we have a free root if our root is a real number? In that case, no. Well, if we find a real root, then we can still take the complex conjugate of the real root, but taking the complex conjugate of a real number doesn't give us another root, because the complex conjugate of a real number is, again, the same real number. So if we find a real root, then we can't apply that theorem to find an extra root. So it only works if our root has an imaginary part. And, importantly, our polynomial has real coefficients. So in that case, if we have a real root, then what we would do is we would just divide by the linear factor. So for example, what we could have done in this example was see that f of what was one of the real roots, f of minus 2 is 0. Since minus 2 is a real root, we don't get an extra root, so all that we would then do is divide by this factor that we know. So x plus 2 is a factor, and then repeat. Okay, the point is it only works if the root that we have has an imaginary part. Okay, let us return to this example. We know we're looking for 9 complex roots counted with multiplicity. Okay, let's take a look at our polynomial. Notice it has real roots, so maybe we can try that trick. Let's take a look here. If we take out a x to the 5 here, we're going to end up with an x to the 4 here, and that might look like that part that we have over there. So maybe let's take out an x to the 5. then what we have, x to the 4 plus 1, and let's write it this way, minus x to the 4 plus 1. That's the same. So let's factor out that. That's x to the 5 minus 1, x to the 4 plus 1. So notice here we have a factor, x to the n minus 1, and here we have another factor, x to the, let's say, m minus something else. Let's write it this way, x to the 5 minus 1 and x to the 4 minus 1. So in this case, well, all the roots that correspond to that factor, those are all the fifth roots of 1, and that factor, those are all the fourth roots of minus 1. Okay, and we know how to compute the nth roots of complex numbers. So let's do that. So the fourth roots of minus 1, let's write minus 1 in polar form. So where is minus 1? So minus 1 is over there. What is the argument? The argument is pi. So we write minus 1 in that form. And what do? We add multiples of 2 pi. So up to k, where k is an integer. And to obtain the fourth roots of minus 1, we divide by 4, and we let k be in any one of the integers 0, 1, 2, and 3. So here we have the fourth roots of minus 1. And if we write them out, they are e to the I pi over 4, e to the I pi over 4 plus pi over 2, e to the I pi over 4 plus pi, and e to the I pi over 4 plus 3 pi over 2. So here are the fourth roots of minus 1. And these numbers correspond to the roots of this factor of the polynomial. So x to the 4 minus 1. Okay, so those are those 4 roots, but we're looking for 9 roots. And where do the other 5 come from? They come from the fifth roots of 1. So we also need to calculate the fifth roots of 1. So the fifth roots of 1. Let us write 1 in polar form. So that is I, and the argument is 0. So where is 1? 1 is over there. What is the argument? Is 0. Let us add multiples of 2 pi. So 2 pi times k. And we divide the argument by 5 because we're taking the fifth roots of 1. And k should then range from 0, 1, 2, 3, and 4. So let's write out the fifth roots of 1. That is e to the I 0, but that is just 1. e to the I 2 pi over 5. That is the second fifth root, e to the I 4 pi over 5, e to the I 6 pi over 5, and e to the I 8 pi over 5. So let's see, there are 1, 2, 3, 4, 5 fifth roots of 1. So the roots, so the 9 roots of f of x are the 4 fourth roots of what was in -1, of -1, and the 5 fifth roots of 1. And here we have written out, here are the 5 fifth roots of 1, and here we've got the 4 fourth roots of -1. And those are the 9 roots of f of x. So notice here, what did we do in this example? We saw that there was some pattern that we could exploit if we cleverly factorize our polynomial, and we saw that we ended up with some nice factors here of the form x to the n minus some complex number and x to the m minus some complex number. And we know what the factors or what the roots of polynomials of that form are. They are the fifth roots of 1, and over here the fourth roots of -1. Okay. So that is that example. Let me take a look at the chat. There is nothing in the chat that I should address. Let's take a look at the next example. Find all the roots of the following polynomial. F of x is 2x cubed plus 5ix squared minus 4x minus I. Okay, so now we have to be careful. Our polynomial does not have real roots. So let me rephrase that. Our polynomial does not have real coefficients. Not all of the coefficients of the polynomial are real. So we cannot apply that trick. If we find a complex root, then the complex conjugate is not necessarily a root, because here we have a coefficient that is not real. It has an I in it. Okay, so be careful there. So how many roots are we looking for? So by the fundamental theorem of algebra, we're looking for 3 roots. F of x has 3 roots. With multiplicity, counted with multiplicity. Okay, let's take a look at our polynomial. We don't really see any pattern that we can exploit, so let's go into guessing some roots. So let's guess some roots. So let's guess f of 1. What is that? 2 plus 5i minus 4 minus I. And we can already see the real part is -2. So that's not 0. So 1 is not a root. The reaction to that is... okay, so we have to get again. We have to guess again. So let's try minus I. let's see, that is 2i minus 5i plus 4i minus I. And that is 0. So here we've got minus 6i plus 6i is 0. So minus I is a root. And now we have to fight the temptation to say that I is also a root. We cannot say that I is a root because our polynomial does not have all real coefficients. So we're not allowed to say that I is a root. So, okay, what are we going to do? We're going to divide by x plus I. So the linear factor that corresponds to the root minus I. So 2x, what is our polynomial? 2x cubed plus 5i x squared minus 4x minus I. And we do our long division. We should get a 0 remainder because x plus I must be a factor. And our quotient is 2x squared plus 3ix minus I. So we can write f of x as x plus I multiplied with 2x squared plus 3ix minus 1. Okay. So now we still need to factorize this quadratic. But notice here this quadratic also has a complex coefficient in there. So the best way to factorize a quadratic that has a complex coefficient in one of its coefficients is to complete the square. So what we will do is we will complete the square of that quadratic. Of 2x squared plus 3ix minus I. Okay, and by completing the square, what do? We are going to write our polynomial in the following form. I'm going to put some brackets, and we're going to put the constant term way out there. Okay. And now we're going to ask what should we square to get what we're looking for here. So what we will do is we will add and subtract some terms here. And what do we want? We want to know, well, what should we square to get that? Well, we know for this term, what should we square? We should square square root of 2x. Okay. And now for to get what we're looking for in the middle here, now think of what happens when we square a bracket like this. We multiply the two terms inside together, and we multiply by 2. So what should we have? We should have a 3i, and we should get rid of the square root of 2, and when we multiply by 2, we should get 3i. So that is what we're looking for, 3i over 2 square root of 2. So let us just see if we're going to square this thing. What are we getting? So square root of 2x, we get 2x squared. That's fine. To get the middle term, multiply these two together, multiply by 2. So that is going to get us 3ix. Okay, fine. And now let's add and subtract the squares that we are going to get there. So what do we get there? That is minus 9 over 8. And we're going to immediately subtract the minus 9 over 8. Okay, and what are we left with here? This is 9 over 8 minus 1, which is 1 over 8. Okay. So there's a question in the chat. Two questions in the chat. One from Tariro to Window. Can we also use the quadratic formula? You can, but that is slightly dangerous because you will have to interpret what is meant by the square root of things like the square root of a complex number. So that is slightly dangerous. And if you think about it, the quadratic formula is essentially completing the square. So to answer your question, yes, you can use the quadratic formula, but it is slightly dangerous because you might run into trouble in the interpretation of the square root of a complex number. And then there is a request to explain the last step again. Well, we are completing the square. So what we're doing is we are moving the constant part away, and we're leaving some spaces. We are adding and subtracting some term here. And what term are we adding and subtracting? Well, it is the term that exactly makes this term into a square. So what we then do is we ask, well, what is the square root of this term? That gives us the square root of x. And now we ask, what should we multiply this term with and multiply by 2 to get that term? So that is how we get this term. And so now we see if we work out this square, then we get that over there. And then just to keep everything balanced, we add and subtract the extra term there. Okay. So let us continue. So we're looking for the solutions to when this is equal to 0. So let us introduce an auxiliary variable. So let's call it, so let w be square root of 2x plus 3I over 2 square root of 2. Then we're looking for solutions of w squared plus 8 is equal to 0. Or in other words, we're looking for the roots of the polynomial w squared plus 8. And that is, of course, the two square roots of 1 over 8. So what are the square roots of 1 over 8? No, minus 1 over 8. Apologies. So we are looking for the square roots of minus 1 over 8. So what are the square roots of minus 1 over 8? That is I over the square root of 8. And w is minus I over the square root of 8. And now we plug back in what we defined. w as, and we solve for x. 3I over, that is also the square root of 8, which is I over square root of 8, and square root of 2x plus 3I over square root of 8 is minus I over square root of 8. And we solve for x. We get that x is minus I over 2, and x is minus I. Okay, so now we have found all the 3 roots. So we're looking for 3 roots. Now we found all 3 roots. So the 3 roots of f of x are, they are what? The first root that we found was minus I. And here we have another minus I, and I over 2. So notice here we have a repeated root. So minus I occurs with multiplicity 2. So minus I occurs with multiplicity 2. Okay, let me take a look at the chat. There is a question from Rutendo. Can we please explain how we got the minus 9 over 8? So that comes from this term. So that is the square of that term. So do revise, please, completing the square. So it's not very difficult, but it does require a little bit of practice. So do revise completing the square. So the entire point is we want something that if we square it, we get those terms. And then we add and subtract the extra terms there. So what we do is we disregard the constant term, and we want to add and subtract something so that this bracket we can actually factorize into a square. Okay. So this one was a little bit trickier because we needed to use, we needed to complete the square. Let's do another one. Exercise. Find all the roots of the following polynomial. F of x is x to the 4 minus 5x cubed plus 10x squared minus 10x plus 4. Given that 1 plus I is a root. Let's say root of f of x. Okay. So we see here our polynomial has all real roots. So if we have a root, then if we have a complex root, then the complex conjugate is also a root. But we're given a complex root. So we immediately get a root for free. So let's see. How many roots are we looking for? We're looking for 4 roots. So by the fundamental theorem, algebra, f of x has 4 roots with multiplicity. Okay, since all coefficients of f of x are real, and 1 plus I is a root, 1 minus I is also a root. So the following polynomial is a factor of f of x. So x minus 1 plus I and multiplied with x minus 1 minus I is a factor of f of x. So if let's multiply out this polynomial, what do we get? This is x squared minus 2x plus 2. So what will we do? We will divide f of x by this quadratic polynomial, 2x plus 2, and f of x is x to the 4 minus 5x cubed plus 10x squared minus 10x plus 4. And this is actually the long division that we did at the beginning, or just before the lecture started. The quotient is x squared minus 3x plus 2. So please do that long division. So what do we get? We get f of x is, we can factorize it as follows: x minus 1 plus I, x minus 1 minus I, multiplied with then the quotient that we get if we divide by that, not 2x squared minus 3x plus 2. And let's see this quadratic. Oh, that one factorizes fairly easily. So that one factorizes that one factorizes 2x minus 2 x minus 1. So the roots are 1 plus I, 1 minus I, 2, and 1. So the 4 roots, so the 4 of f of x are 1 plus I, 1 minus I, 2, and 1. And see here, we again use that little trick to get a root for free. So we know that 1 plus I is a root, and all the coefficients of f of x are real. So the complex conjugate is also a root. So we get a root for free. We divide by the polynomial that we know is a factor to get the quotient, and then we factorize the quotient. And luckily enough, this quotient factorizes fairly easily into x minus 2 times x minus 1. Okay, so that is the final example that we will discuss. Let me just take a look at the chat. There is a question about the previous question. How did we find I squared root of 8 and I minus I squared root of 8? That is because, notice here, we're trying to solve this equation. We are finding the square roots of minus 8, or the 2th roots of minus 8, or minus 1 over 8. So please do revise chapter 6 in finding the roots of complex numbers. So the one of the square roots of 1 over minus 8 is I over the square root of 8, and the other square root of 1 over minus 1 over 8 is minus I square root of 8. So it is very important to be able to find the roots, the nth roots of complex numbers. Okay, so now we've discussed a whole bunch of examples in finding the roots of, finding all the roots of polynomials over the complex numbers, and we've discussed some of the strategies to do that. The hardest one is probably completing the square. If you're rusty with completing the square, do look up completing the square and do some exercises on completing the square. Okay, and with that, ladies and gentlemen, that finishes our discussion on chapter 7. So we have now discussed all of the chapters in the textbook. So this will be our final lecture. So all that remains is to wish all of you all the best in your coming exam, not just for WTW 1 to 4, but in all your exams that are to come. So we're all holding thumbs for you in your coming exam. There's nothing that makes us happier than when our students do well. There's a question about the scope of the exam. That will be in the Monday announcement that will go out today. Okay, and with that, let us leave it there. I wish you all a lovely Monday. Please remember that there are still tutorials, so please go to your tutorials. Please don't neglect your homework. And with that, lovely Monday for everyone, and all the best for the exams. Goodbye, everyone.